0.5 degrees at the deep sea end. Yeah, why this cold water? And exactly because we have a senior colleague who is working on process, so he's a better person to explain you. I'm from the structural background.
So how much water you generate about?
Yeah.
How much water you produce?
So in Lakshadweep, the depending on the population of the islands, each maximum population is 11,000 per island. So that's in the capital city, that's Kavaratti Island. So for that, we have 1 lakh liter per day as the capacity, 1 lakh liters per day, and that is self-powered. So it is running as long as the temperature difference is available in the sea. Only for starting of the plant, we will be using the grid connection. Once the equipment starts, pump starts running, it will be totally free of the grid. And in case, if we, at some point in time, if you want to generate more water out of the same plant, then it can be, the turbine can be bypassed for some time. The plant can be put on the grid. Then you can get 1.5 lakh liters per day from the same plant. Thank you all.
The last paper of this session is cost of energy in a vessel, that is assessing likely applications in marine transport where shift to electric will succeed without other intervention. This will be presented by Mr. Sandit Thandasari. Sandit Thandasari is the founder CEO of Navalt Solar and Electric Boats, the firm that built India's first solar ferry and recently the largest and fastest solar boat as well. Now in the process of completing landmark project in defense, fishing and ROROs, all solar electric. He is a graduate from IIT Madras and an MBA from INSEAD. He is also an author of the book Solar Electric Boats, published by ETN. He is a winner of numerous awards. Some of them are Gustave Trauve Award for World's Best Electric Ferry, Solar Impulse, Innovators of the Year from TIE, GCIP, Wilgrow, Tissot, and Prime Minister of India. With this, I welcome Sri Thandasari to present his paper.
Good afternoon, everyone. So today morning, our chief guest, Professor Gokran, made a very important statement regarding the adoption of technology. And he used the word commercialization and economics. So fundamentally, any technology, let it green technology, will only take in a big way if the economics work. Otherwise, subsidies and pilot projects can only take you so far. So today I want to speak from a perspective of economics. And the first step in economics is operating expense, because capital expenditure in many projects can be managed. But the first step is OPEX. And one of the driver, or the most important driver, is the cost of energy. So just to set the context, when we talk of vessel, it could be boats, small ships or large ships. And then in terms of energy need, we are discussing propulsion, which is what is required to move the ship or vessel, and everything else we can term in auxiliary energy, which is HVAC, lighting, controls, everything else. Now in any vessel, we can think of 5 energy sources. So whether it is battery, which stores the grid energy, solar, and the wind, which could be wind to thrust, or wind to turbine, electricity side. Any fuel cell, which could be hydrogen or any other fuel, and an engine, typically, traditionally diesel or any other fuels, which can convert either mechanical energy or in a generator into electrical energy. So this is the landscape. So why I use those 3 sizes is, depending on the sizes, the technologies and the current state are different. So if you take a smaller vessel, Mostly it can work with solar and battery, most applications. Only when the energy need is high because of range and speed, maybe we go to hybrid. Whereas in the near term, at least the smaller ships can now run in this combination already. The larger ships is still a bit longer away to make it green tech, completely green tech. But it will be driven largely by some liquid fuel, not necessarily hydrogen, some liquid fuel. It could be ammonia, as was described today morning. Now, when we talk of cost of energy, if I put all the five sources of energy, the driver of the cost is the input cost. For example, in the first case, whether it's battery, the input cost is a cost of grid. Like in India, it is 7 rupees is a grid cost, let's say. Then you go through certain efficiencies, whether it's battery efficiency, system efficiency, to get the what we call as electrical energy cost, what I represented as CEEB, which is cost of battery or electric from a battery. Then if it's in a propulsion side, then you also introduce the efficiency of motor. I'm just telling the methodology to arrive at the cost of any energy source. So if it is a fuel cell, there is a specific fuel cell efficiency, system efficiency, motor efficiency to get the cost. With this, of course, solar and wind, the OPEX side is zero, so it's zero anyways. Engine, of course, there is an SFOC of the engine. If it's an alternator, you also have the alternator efficiency, things like that. So it's a very straightforward way to compute the efficiency and thereby the cost of energy source, which is electrical or mechanical from any of these. If you take across the world, in this there are about 133 countries taken. So if you take cost of grid as one parameter, and the second parameter is cost of fuel. So CFO is a cost of fuel. It's all in US cents, so since it's an international conference, but just put 0.85 and you get the number. So these are very high spread countries. The spread here is difference between cost of, let's say, propulsion energy from a battery compared to cost of propulsion energy from an engine. So that is ranked like that. So these are really high difference countries. An example is Norway is taken for a bit more deeper analysis. India comes in the 41st ranking, you can say, but still on the highest side. So it's 125, which is about 100 rupees diesel versus about 7 rupees grid. So that's the number. Then there are a bit lower like Saudi Arabia or US, specifically California. The spread is very low, which also means it is so difficult to shift to electric. I'll come to that anyway. Now, if you just take those 4 examples for the purpose of analysis and just put down these numbers and then run through the same analysis of cost of energy, which I described earlier, what you will get is for each of these countries, if you take the fuel cost, grid cost, you can find the cost of auxiliary energy. So this is the cost of auxiliary energy. From battery side, it is 15. From engine, it is 80. So this gives that spread. So why I tell this, or why this is important is, more the spread, it means the savings are more. So when you shift from engine to battery, if the spread is more, the adoption is more. So the simple rule is, the higher the spread, the higher the diesel cost, and the lower the grid cost, electrification works. So in this example, Saudi Arabia, there is almost no chance of shifting to electric unless there is a subsidy or other play. That's a different thing. But by pure numbers, this should not shift to electric. So even US, California, electric boats or electric car technically shouldn't work unless the subsidy comes into play. But California has a lot of electrification, which is a different thing because of a lot of subsidy element. India has a very good spread and it works. Now, another important insight is so if I go to the previous slide, one observation you can take is difference between battery and diesel here. Let's say India, for example, 11 and 50, which is 39 cents, about 35 rupees, let's say. Whereas the propulsion is 28. In all the countries, you would notice that this difference, which is plotted as darker blue is auxiliary, the lighter blue is propulsion. always auxiliary is higher than propulsion. So it's a very simple decision for the government to take. Auxiliary is much more economical to shift than propulsion if you have a choice of just one. So it is not just OPEX, and I showed the OPEX part. When you do electric propulsion in propulsion side, the regulations are much more stringent. So the capex also is higher when you do propulsion. So almost always any vessel, whatever program government runs, do auxiliary first, then go to propulsion. And of course, you should do both ideally. And then fuel cell. There is a lot of talk of fuel cell and the source of hydrogen. So today there is no price realization in any country. If you go to in Europe, if you have a Mirai car, you can go to a pump and put it, I think it's 10 euro. Last time, at least in Germany, I checked that number, it's 10 euro. It's still on a very high scale. I just put three numbers, 5 USD per kg, which is a very optimistic scenario today. It doesn't exist. Technically, it can, because theoretically, 1 kg of hydrogen by electrolysis, if the solar cost is 2 rupees, if you can get the solar cost at 2 rupees, you technically need about 40-45 kilowatt hour energy to do the electrolysis, which means about $1 is the cost of electrolysis, then there is a compression, etc. So you can get here today, maybe near term 3 and a very long term 2. Adani, IOC, Reliance have all announced $1, which is theoretically impossible today unless you get a solar under 1 rupee. That's a different matter. The important point is these numbers, it throws already 43 cents for auxiliary. And if you see earlier, hydrogen works in certain applications where the battery do not work. Because always battery is cheaper than hydrogen. Hydrogen has an added issue that even the capex is ridiculously high, at least today. But in certain application, battery will not work and thereby you need hydrogen. So that's where we should take care. When in the previous slide, California hydrogen works whereas battery doesn't work very well. So that's, anyway, it's more to do with difference with fuel. So again, hydrogen also same property, auxiliary first, then propulsion because of the same savings. If you look at all the countries, one thing is about 84 countries can switch to hydrogen at today's price compared to diesel, not with battery. Whereas as it reduces, the number of countries increase to almost 125. So in the long term, hydrogen works very well for most countries in those applications, not in every application. In practice, in reality, all systems are work in a combination. So I gave each individually. Now when you do combination, so there is a grid battery, there is fuel cell, there is auxiliary engine, all generating electricity. Then there is solar, there is wind turbine. There is engine giving mechanical energy and motor giving mechanical energy, plus wind to thrust. So these are all, in reality, you can have all these. So the way to compute in combination is to look at the contribution of energy, like any logical way to weighted average you do. You do the contribution by ratio to get these numbers. To give it a number in practice, I will give an example of a diesel ferry, electric ferry, and a solar ferry. These are actual boards. So example is the Aditya solar ferry. 67% of its energy is from sun. This is data for now 7 years. So 67% is from sun, 33 is from grid, which means the cost of mechanical energy, what you get from motor, is about 4 cents, 4 US cents, which is about 3.5 rupees, you can say. Whereas in a pure electric ferry with a grid cost in India, this is all India numbers, this is about 12 cents. And a very efficient diesel is 40 cents. So 4, 12, 40. So it's a 1/3 reduction when we shift from diesel to electric in India. And another 1/3 if you shift to solar, provided the solar contribution is 67%. This works in slower speed ferries, not in fast ferries. Contribution of solar cannot be 67. That's also an important caveat. So here I have ignored the fact that in India, traditional diesel ferries are highly inefficient, which Dr. Opisha mentioned about how CFD optimization helps. So traditional diesel ferry has another problem, that it's built of steel or aluminum, that you may have another 3 times saving. So typically, when we put Aditya numbers is 1 by 35. So this shows at 10 times. The 3.5 additional is because traditional has about 3 times inefficiency. That's to do with the choice of material. Then I just want to briefly touch upon hybrid. Again, many applications cannot be pure electric. You need to go hybrid. So it is either series hybrid, which means motor only is connected to propulsion, or in parallel where both are connected either in same shaft or in independent shafts. Between the two, the important thing is between the two, which is better, which is cheaper. So if you notice here, the cost of mechanical energy from a series hybrid is 34 cents, whereas a parallel hybrid is 26. The reason is the cost of energy from here is about 50 cents versus 40 cents here, and that's the driving factor. So which means in a series hybrid you are having an additional conversion of mechanical energy to electric, and that is what driving the cost. So almost always parallel hybrid will have a lower operating expense. It will also have a lower capital expenditure because in series hybrid the motor is as big as your propulsion need, whereas in parallel hybrid you can make it smaller to the need on the zero emission mode, like Sri Opisha mentioned about the in a tug case where you can have a motor which is smaller than the total requirement. So always choose parallel hybrid when it works compared to series hybrid. There are certain applications where this will not work, then of course you have a different choice. So this is the other insight, and I just want to summarize these 6 insights you get just by looking at the cost of energy, which is spread between diesel and grid will make the electrification. Auxiliary first, both in shift to electric or shift to fuel cell. The long-term green hydrogen will work in many applications. And solar can significantly lower OPEX in especially applications where the contribution is higher, which is more like slow speed, and applications where it work parallel is cheaper. So these are some of the insights you can get. The more complex is go to capex and total cost of ownership, and that is a different session, different time. Thank you.
Yeah, please.
Yeah, please. Can you? Yeah. Yeah. So, in this study, this calculation has nothing to do with it. This is the cost of power that goes into the propeller. That has nothing to do with what boat I do or nothing. It doesn't matter. It's a cost of. Huh. Hmm. Okay. Ah. No, no. So you are confusing. Although I mentioned solar free electric ferry, even if let's take the electric ferry you talked about, the cost of mechanical power in a system is same irrespective whether I do a fast or slow. The contribution may be important. What you say, the contribution of solar is what drives the cost. So, which is why I used the word about 6 knots vessel. It is possible to do 67%. In faster vessel, 67 is not possible. 67% from sun is not possible. Yes. 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 Which part? Which part is not clear? There is only one way. There is input cost. The only point where you say is in this number 67% is dependent on the kind of vessel. And I told very specifically it is for slow speed vessel. These equations hold good for any vessel, it doesn't matter. We can discuss directly. So you had something? Ah,
There is a query. Actually, the energy cost we have considered for solar, electric, and diesel.
yes.
Here we have considered only the energy cost.
Yes.
Suppose we are considering the maintenance as well.
Yes.
How the variation is going to be?
So between solar and electric, almost same because both have electric system. Solar is in addition, which typically has very low maintenance. Solar panel, you don't do any maintenance per se. So there is no incremental maintenance by putting solar on the vessel. So, but it's a small number on both solar and electric, the maintenance cost itself on the OPEX level.
Well, coming to the electrical,
Ah.
battery replacement.
So, of course, which is why I said the next level is looking at the life cycle cost, which have both the energy cost, all the other maintenance, battery replacement cost, capex, everything is there. That's a much more deeper analysis. That is the next step which should be done. I totally agree with you. Yes.
In this paper you have named as a ferry, Aditya Solar Ferry.
Ah.
So that is designed for what?
6 knots, 6 knots. 6 knots. Yeah. Yeah, only at that 6 knot, which is I want to very clearly say to Opisha sir that at 6 knots is what the 67 works. I gave the example of 6, and I clearly tell in a faster ferry, 8 knots, 10 knots, that 67 is difficult to achieve. You cannot achieve because sun is fixed by the area, so the percentage will keep dropping as the energy need increases.
The operation profile of the vessel is also important, right? The operation profile of the vessel is also important.
Which is what drives that 67%. Like so Aditya case, it runs from 7 to 7, about 70 kilometers in a
I'm
day.
talking about the one per yeah, per hours. That is also important.
That will come here,
67.
nowhere else. It will drive that 67%. So if you're running fast, or if you're having a longer range in a day, the 67 will drop down because solar is fixed.
So this comparison with respect to the same operation profile,
It is just one example of Aditya. If it were electric, if it were diesel,
with same operation.
same.
You are only considering the OPEX, not the CAPEX.
Yes, cost of energy is only OPEX. Cost of energy means only OPEX.
Only the OPEX part. So when you replacement of the battery or
Yeah. This is not life cycle cost, only OPEX. Only cost of energy, not even OPEX. Thank you, sir.
The last paper is a very good paper for discussion during the tea break. With this, we come to the end of this session. I think all four papers were very interesting because it enthused the listeners so that there were a lot of questions and discussion. So that's all, sir. Thank you. You will give? Oh, okay.
Uh, for, uh, to who was the first speaker? Richard is not here. Okay. Mr.
Yeah,
Sri
I'm
Rajkumar.
still online.
Sri Rajkumar, could you come for the memento, please? Shri Abhijit. Abhijit Sajjan.
Sajjan.
Yeah.
Mr. Sajjan.
Yeah, he's coming.